For decades, there's been this one single question that's just dominated the entire world of quantum computing. It's a question that's fueled billions of dollars in research and, let's be honest, a whole lot of panic. And that question is this: will a quantum computer break the internet? I mean, the fear, right, is that some super powerful quantum machine could just crack the codes that protect everything. We're talking about our banks, our private messages, the whole shebang. It's always been framed as the ultimate promise and the ultimate threat of this new quantum age. For years, pretty much everyone in the know said the answer was yes. It was just a matter of time. But what if they were wrong? What if that entire assumption is built on something that's, well, physically and mathematically impossible? Today, we're diving into a really powerful new analysis that says the dream of quantum factoring isn't just delayed, it might be dead on arrival. So, this idea has a name, the terminal descent hypothesis. And the core argument is that when it comes to the one thing everyone's worried about, breaking encryption, the entire field is caught in a trap with no escape. Okay, so to really get what's going on, you have to know that the industry has been chasing two different paths to get this done. Think of it like a pincer movement. On one side, you've got the original, super elegant approach, Shor's algorithm. And on the other side, there's a newer kind of brute force method using what are called heuristics. The bombshell claim of this hypothesis: both paths are dead ends. And this is the trap. It's an impossible choice. Shor's algorithm, the classic, it needs a level of control over the physical world that we might just never be able to achieve. It's a physics problem. So what about the backup plan? While the heuristic approach gets rid of the precision problem, but it creates a new problem, a mathematical complexity so insane that it completely kills any quantum speedup. You're trapped. So let's start by looking at that first wall, the precision problem. Right, so this is what we're calling the precision wall. It's the first jaw of that pincer trap. And the argument here is that Shor's algorithm, the one everyone talks about, just can't be built in reality. And it's not about not having enough qubits. Everyone thinks it's about qubit count. It's not. It's about how well you can control them. Okay, let's talk numbers for a second, because this is where it gets crazy. If you take our absolute best tech, I'm talking the most advanced electronics, shielded inside the coldest fridges on Earth, the best control we can possibly get is about 1 part in a billion, 10 to the minus 9. That sounds amazing, right? Incredibly precise. Well, hold on. It's not even in the same universe of what's needed. To break a standard RSA 2048 encryption key, the stuff that protects the internet, Shor's algorithm has to be able to tell the difference between quantum states that are this far apart, 2 to the power of negative 2048. That's not a number with 9 zeros after the decimal. It's a number with more than 600 zeros. The gap between what our best tech can do and what the math demands isn't just big, it's astronomical. Now, I know what you're thinking. What about quantum error correction? That's supposed to fix all this, right? Well, here's the thing. Error correction is fantastic at fixing random one-off mistakes. It's like finding and fixing a typo in a huge book. But that's not the kind of error we're talking about here. This is a tiny, systematic error that happens on every single step. It's less like a typo and more like your compass being off by just 1 degree. On a short walk, no big deal. But on a cross-country journey, you end up in a totally different state. And this is the killer point, directly from the analysis. Quantum error-correcting codes, they just aren't built to handle this kind of error. They can't suppress it. So this tiny, systematic, off by 1 degree error just builds up and up and up with every single calculation until your final answer is complete garbage. This one physical limit basically shakes the entire foundation of what we call fault-tolerant quantum computing. Okay, so if Shor's algorithm hits this physical precision wall, what about Plan B? The industry's big pivot has been to try and turn factoring into a different kind of problem, an optimization problem. But, you guessed it, this just leads you into the other side of the trap, and this one might be even worse. When you reframe factoring this way, you create a mathematical landscape that scientists call a spin glass. The easiest way to picture this is a gigantic, super rugged mountain range. There are thousands and thousands of little valleys that all look like they could be the lowest point. They're tempting false answers. But there's only one true lowest point, the real solution, and it's hidden somewhere in that massive, confusing landscape. And it gets even worse. As you scale up to bigger numbers, the ones that are actually hard to factor, this rugged landscape develops something called a barren plateau. All of a sudden, your algorithm finds itself in the middle of a vast, featureless, perfectly flat desert. There's no slope, no hills, no valleys, no clues whatsoever telling it which way to go. It's completely and totally lost. And trying to find the solution in that barren plateau, it's like trying to find one specific grain of sand on a vast, flat beach while you're blindfolded. That's the problem. The landscape is giving the algorithm zero information, zero feedback. It's a completely futile search. So what's the consequence of all this? Well, to have any hope of finding your way, you'd have to take an exponential number of measurements just to get the faintest hint of which direction to go. And that cost, that exponential number of tries, completely wipes out the entire reason you were using a quantum computer in the first place. Any quantum speedup is just gone. You're right back where you started, with a brute force search that's no better than a classical computer. Plan B has officially failed. But wait, there's more. It's not just that the quantum approaches are hitting these fundamental walls from the inside. The trap is closing in from the outside, too. Because while all this has been going on, classical computers have gotten shockingly good at simulating quantum computers. This is the third and final piece of the puzzle. It's a concept called the simulation singularity. And the idea is pretty wild. It's the point where, just as a noisy, real-world quantum computer gets powerful enough to do something interesting, some smart programmer on a classical computer figures out a way to simulate the whole thing, but faster and better. And this isn't science fiction. Just look at the QREC simulator. Right now, it can simulate a 54-qubit machine with high fidelity on a single GPU, a single graphics card. You might remember, 54 qubits is around the number Google used for its huge quantum supremacy announcement back in 2019. Now you can basically do that same work with off-the-shelf hardware. It's incredible. For the kind of noisy, medium-sized quantum computers we have today, classical simulation is already winning. And this leads to a truly devastating paradox. To get any of these fancy algorithms to actually run on today's noisy quantum hardware, you have to simplify them. You have to cut corners, make approximations. But here's the kicker. The very approximations you have to make to get it working on a quantum chip are the exact things that make it easy to simulate on a classical one. It's like there's no sweet spot. There's no Goldilocks zone where a problem is simple enough for our current quantum machines, but still too hard for a classical computer. So let's put it all together. You've got the precision wall, which is a physics problem. You've got the heuristic trap, which is a math problem. And you've got the simulation singularity, which is a classical computing problem. When you see all three forces closing in, the future of quantum computing starts to look very, very different. So let's just recap the three pillars of this whole terminal descent idea. First, the precision floor. Physical reality puts a hard limit on control, making Shor's algorithm impossible. Second, heuristic failure. The backup plan gets hopelessly lost in barren mathematical deserts. And third, the simulation singularity. Classical computers are just getting too good at faking it, erasing any advantage. And you know what's wild? If you look closely, the big players in the industry almost seem to be confirming this themselves. You see Google talking about a bottleneck and finding any real-world advantage. You see IBM quietly shifting its language away from error correction, which is what you'd need for the big stuff, to error mitigation, which is basically a less powerful short-term fix. It feels like you're watching a strategic retreat happening in plain sight. So what's the takeaway here? Is quantum computing just useless? No, not at all. But its real purpose might be totally different from the hype. The future probably isn't some quantum apocalypse where all our encryption is broken overnight. It's more likely a hybrid niche, where these amazing quantum devices work as specialized co-processors for very specific scientific problems, like discovering new drugs or materials. You know, problems that don't need that impossible 600 decimal place precision. So, in the end, the quantum revolution isn't what we thought it was. Breaking the internet was the big, flashy promise that launched this whole thing. But if that promise is an illusion, it makes you wonder, what is its true, more subtle purpose? The journey, it seems, isn't about destroying our digital world, but maybe, just maybe, about building a new physical one molecule at a time.